Earth feels enormous when standing on its surface. Oceans seem endless. Mountains feel ancient and immense. But in the true scale of the universe, Earth is almost impossibly small, smaller than most minds ever picture. Tonight, this journey moves outward through the solar system, the Milky Way, and the deepest cosmic structures to reveal just how tiny our world really is. If this kind of calm space documentary helps with sleep, relaxation, or quiet learning, please like the video, subscribe to the channel, and settle in for the scale of everything. The largest region that science can describe around Earth is not the whole universe, but the observable universe. This is the portion from which light, or other signals that travel at the speed of light, has had time to reach Earth since the beginning of cosmic expansion. Observations show that the universe has been expanding for about 13.8 billion years. At first, this seems to set a simple limit of 13.8 billion light-years in every direction, yet space itself expands while light travels through it. So the most distant matter now seen is much farther away than that early, simple figure suggests. The present radius of the observable universe is about 46 billion light-years, and its diameter is about 93 billion light-years. Earth sits within that measurable sphere, not at a special centre in all of existence, but at the centre of its own observable horizon, because every observer, wherever placed, sees a similar limit around itself. This horizon is not a wall, not an edge made of matter, and not a border where the universe stops. It is a limit created by time, distance, and the finite speed of light. Beyond it, there may be far more space, perhaps vastly more, perhaps even without end on the larger scale that can be described. But observations cannot yet carry reliable information from these regions to Earth. What can be measured remains inside the visible cosmic volume. In that volume there are hundreds of billions, and likely around 2 trillion galaxies if faint and early systems are included in deep counts and statistical corrections. The exact total remains uncertain, because many galaxies are extremely dim and distant, and because estimates improve as telescopes and methods improve. But all careful estimates agree on the same essential picture. Earth belongs to a realm so large that familiar scales stop being useful, long before the outer horizon is even approached. In ordinary life, Earth seems extensive. Oceans spread across basins wider than continents. Mountain ranges rise over long belts of land. Jet aircraft require many hours to cross a portion of the globe. Even at planetary scale, however, Earth is modest. Its diameter is about 12,742 kilometers. Set against 93 billion light-years, that width becomes almost impossible to represent in human feeling. A light-year is the distance light travels in 1 year, nearly 9.5 trillion kilometers. When the diameter of Earth is compared with the diameter of the observable universe, the ratio becomes so small that direct intuition no longer helps. Earth is not merely small in that comparison. It is so small that it vanishes far below the threshold of any ordinary mental picture. A drawing that showed the full observable universe to scale could not include Earth as a visible globe. Earth would be smaller than a point that could be printed. Even the Milky Way, which already seems immense when described in astronomy, becomes only a minor feature at this scale. The observable universe is not mainly a place of planets, or stars, or even individual galaxies. At its broadest extent, it is a domain in which such things blend into patterns of matter and radiation, spread across unimaginable reaches. Earth does not stand as a noticeable object in that field. It does not mark a favoured location. It does not anchor a meaningful geometric position. It is one tiny planet around one ordinary star within one galaxy among uncountable others, all contained inside a visible region whose size is defined by the age and expansion history of the cosmos. The oldest light that can be seen from Earth gives this horizon a deep physical meaning. That ancient light, known as the cosmic microwave background, comes from a time when the early universe cools enough for atoms to form and for light to travel freely through space. Before that time, the young universe is so hot and dense that light scatters constantly. After that transition, radiation streams outward, and part of it reaches Earth after a journey of nearly the entire age of cosmic history. This light does not show an outer shell of matter. It shows the earliest observable surface from which light can arrive directly. In that sense, the observable universe is also a visible record of time. Looking farther away means looking farther back. The horizon is both a spatial limit and a historical one. Measurements from space observatories and large ground-based surveys show that on the very larger scales the observable universe is remarkably uniform. Matter gathers into structure, yet averaged across enough distance, the cosmos looks much the same in one vast region as in another. This uniformity has an important consequence for scale. Earth is not small because it occupies an unusually empty or unusually crowded corner. It is small because the whole visible universe is overwhelmingly large everywhere that can be measured. No shift of viewpoint changes that conclusion in any meaningful way. A planet of Earth's size remains negligible against a region tens of billions of light-years across. The mind often looks for a comparison that will restore proportion, but at this outer boundary most comparisons fail. A grain of sand beside a continent is still too generous. A single cell beside a planet is still too generous. The difficulty comes from the fact that Earth and the observable universe do not differ by a little, or by a lot, but by an almost total collapse of shared scale. The one belongs to the range of worlds that life can cross, map, and name. The other belongs to a range where even the nearest broad measures exceed anything daily thought evolves to handle. What remains certain is simple in its outline. Earth exists inside an observable universe about 93 billion light-years wide. That visible region contains staggering numbers of galaxies and far greater numbers of stars and planets. Its horizon arises from cosmic history and the speed of light, not from a physical edge. Its full extent beyond what can be seen remains unknown. Within that measured immensity, Earth is not a small island in a large sea. It is vastly less than that. It is a world so minute against the observable whole that, at the outermost scale science can presently describe, it effectively disappears. Inside the observable universe, matter does not lie evenly scattered like fine dust in still air. On the larger scales that can be mapped, galaxies gather into a vast pattern often called the cosmic web. This term describes the broad arrangement of matter into long filaments, crowded knots, sheet-like regions, and immense sparse openings. The pattern emerges over billions of years as gravity slowly amplifies tiny differences in density present in the early universe. Regions that begin only slightly denser than average draw in more matter. Regions that begin slightly thinner lose matter to their surroundings. With time, this uneven growth builds a structure so large that single galaxies no longer dominate the picture. Earth, already lost against the observable horizon, becomes even less significant here, because the relevant units are no longer planets or stars, but strands of matter stretching across hundreds of millions of light-years. The word filament refers to one of the long, thread-like bridges in this network. A filament is not a solid rope. It is a broad region where galaxies, gas, and dark matter are more concentrated than average, spread across great distances and joined in a connected pattern. Dark matter is the invisible mass detected through its gravitational effects. It does not shine, but it shapes the formation of visible structure. Ordinary matter, the matter that forms stars, planets, gas, and living bodies, falls into the gravitational framework largely set by dark matter. Because of this, the bright galaxies that telescopes record trace only part of the full web. Beneath the visible pattern lies a much larger hidden scaffold. Large surveys of the sky reveal this arrangement again and again. When astronomers map the positions of galaxies in 3 dimensions, using distance as well as direction, the result is not a smooth cloud, it is a network. Galaxies line up in enormous chains. These chains intersect at dense nodes where clusters form. Between them lie regions with far fewer galaxies. The map resembles foam, lace, or frost spreading over glass. Though each image remains imperfect because the true scale is beyond ordinary comparison. The web is not decorative. It is the natural outcome of cosmic growth governed by gravity, expansion, and the properties of matter in the young universe. At this scale, even a large galaxy becomes a minor point. The Milky Way is about 100,000 light-years wide, yet a filament can extend for hundreds of millions of light-years. A single filament can therefore exceed the width of the Milky Way by thousands of times. The spaces between major structures are also immense. The cosmic web is not dense with matter in the way a forest is dense with trees. It is mostly space, shaped by slight imbalances spread across enormous volumes. Matter gathers along preferred paths, leaving much of the observable universe thinly populated. Earth belongs to one small planetary system inside one galaxy, embedded within this pattern, but at the level of the web, no planet can carry any visible weight in the overall design. The web also shows that the universe is neither random on every scale nor tightly ordered in simple geometric symmetry. Up close, local motions and local histories produce irregularity. On very broad scales, statistical patterns appear, filaments connect nodes, gas flows inward, galaxies form where matter collects deeply enough. This is not a deliberate arrangement, only the long consequence of physical law acting over time. Tiny ripples in density present in the early universe, measured through ancient background radiation, serve as the starting point. Computer simulations that begin with those small early differences and apply known physics grow patterns closely resembling the observed cosmic web. This agreement gives confidence that the large structure now seen develops from the early conditions already measured. Earth disappears in this description in a very particular way. It is not only physically tiny, it is irrelevant to the scale at which the web is described. A map of the cosmic web does not need planets. It barely needs individual stars. Often, it does not even need the internal form of galaxies. What matters is position, clustering, motion, and the distribution of mass across regions so large that light itself takes millions of years merely to cross local portions of them. In a human map, a city can still matter when the continent is drawn. In a cosmic web map, Earth is below the scale of the ink. The material between galaxies also matters here. Filaments contain not only galaxies but also diffuse gas, much of it hot and difficult to detect directly. Observations indicate that a significant fraction of ordinary matter in the present universe lies in this thin intergalactic medium, rather than locked inside stars or planets. Some of this matter sits in warm or hot stretched regions between galaxies and clusters. It does not erase the emptiness of cosmic space. Instead, it shows that the web is a structure of gradients, from denser luminous sites to tenuous reservoirs that still participate in the same gravitational pattern. Because light takes time to travel, the cosmic web is also seen across different ages at once. Nearby regions appear as they are in the more recent cosmic past. More distant filaments and nodes appear as they were much earlier. Surveys therefore combine structure and history in the same map. The farther astronomy looks, the younger the visible web becomes. Yet the same general story remains: matter gathers into a connected pattern rather than remaining evenly smooth. The name web can suggest delicacy, but the forces involved are immense. Whole galaxies fall toward denser regions. Gas heats as it collapses. Clusters grow at intersections. Dark matter halos merge and deepen. Over billions of years, the pattern sharpens without ever becoming static. Expansion continues across the universe as a whole, while gravity gathers matter locally into larger concentrations. Together they shape the broad contrast between structured regions and wide underdense spaces. The result is the largest visible architecture known in nature, seen from this level. Earth is not simply one small world among many. It is a tiny surface on a minor planet around an ordinary star inside one galaxy, carried along a filamentary network too large for direct intuition. The cosmic web reduces Earth by proportion alone. Once the universe is viewed as a web of matter spanning hundreds of millions of light-years, the scale of planets falls away almost completely, and Earth passes beneath notice within the grand connected structure of the visible cosmos. Within the cosmic web, the broadest visible contrast is not between one galaxy and another, but between crowded regions and nearly empty ones. Matter gathers into enormous concentrations known as superclusters, while between them stretch vast underdense spaces called voids. A supercluster is not a single bound object in the simple way a planet or even a galaxy cluster is bound. It is a large region where many galaxy groups and clusters lie in relative proximity within the same broad gravitational landscape. A void is not perfectly empty. It still contains dark matter, thin gas, and some galaxies, but far fewer than average. These two features together reveal the deepest texture of the large-scale universe. They also make Earth smaller by shifting attention away from stars and planets entirely, and toward patterns so broad that a single galaxy becomes only one small mark within them. A void can span tens to hundreds of millions of light-years. In such a region, matter is spread thinly compared with the cosmic average. Galaxies exist there, but they are sparse and often more isolated. The darkness of a void is not a darkness that could be seen as a black cavity cut into space. It is a statistical thinness, a region where the great rivers of matter do not gather strongly. When astronomers map many galaxies at once, the voids appear as wide openings between filaments and dense nodes. They help give the cosmic web its cellular shape, like bubbles pressed together in a giant foam. Earth, inside one galaxy in one denser region, is separated from these immense sparse domains by a difference not of local experience, but of cosmic geography. Superclusters occupy the opposite side of this pattern. They are large assemblies of galaxy clusters, groups, filaments, and surrounding matter, extended over hundreds of millions of light-years. Some names used in astronomy refer to historically identified regions of high galaxy concentration, while newer maps use velocity data and distance measurements to trace more carefully how galaxies move within broader flows. What remains consistent is that the densest large regions are not smooth blobs. They are intricate landscapes in which matter streams along filaments toward greater concentrations. A supercluster is therefore less like a single island, and more like an enormous watershed spread across the cosmos, with galaxies moving under gravity through a shared terrain. This change in scale matters deeply. A galaxy cluster already contains hundreds or even thousands of galaxies. Yet a supercluster organizes clusters themselves into a larger setting. A galaxy like the Milky Way, impressive when considered alone, becomes one member of one group within one cluster-scale environment inside a much greater region. Earth then sits another full step lower, far below the level at which superclusters are even described. Its physical existence remains real, but in terms of large structure it has no independent significance. It is part of a planet, within a star system, inside a galaxy, within a group, inside a concentration whose size erases any local sense of centrality. Voids and superclusters are not added later to an otherwise finished universe. They develop naturally as structure grows from early density variations. Regions that begin slightly richer in matter draw in more surrounding material and grow denser over time. Regions that begin slightly poorer lose matter outward and become emptier. This contrast increases slowly across billions of years. Expansion stretches the overall fabric of space, while gravity locally enhances differences. The result is not chaos but patterned inequality. Matter gathers where gravity can deepen its hold, and leaves behind broad spaces where little remains to build large concentrations. The sizes involved are severe enough to alter even the meaning of emptiness. On Earth, an empty field is still full of air, dust, moisture, microbes, and light. In astronomy, a void remains richer than perfect nothingness. Yet it is empty by cosmic standards because galaxies are rare and mass density is low. This emptiness is measured across regions so large that light needs tens of millions of years or more to cross them. A signal moving at the fastest known speed still requires geological ages, far longer than human history, merely to traverse one of these sparse domains. The scale itself strips Earth of proportion. The inhabited surface of a small rocky planet does not merely occupy a minor place. It belongs to a realm too tiny to register when the universe is described through voids and superclusters. At the same time, the great crowded regions are not compact in the everyday sense. Even within superclusters, galaxies are separated by large distances. Space remains overwhelmingly open. The density is higher than average, not close-packed. This is important because it shows that the universe does not become thick with matter, even in its richest large regions. Most of the cosmos is spacious beyond ordinary imagination. Matter structures the universe without filling it. Galaxies collect into patterns, but those patterns still leave enormous distances between their luminous parts. Earth, though solid and substantial to its inhabitants, exists in a cosmos where almost everything is interval. Observations continue to refine how large structures are identified and how their boundaries are defined. Some supercluster labels depend on mapping where galaxies are most concentrated. Others depend on how galaxies move through the expanding universe and whether their motions indicate shared gravitational flow. Because of this, the exact edges of a named supercluster can remain somewhat uncertain. What is not uncertain is the underlying reality that the large-scale universe contains gigantic dense regions and gigantic underdense ones. The broad contrast is secure even when details of classification improve. The existence of vast voids also carries a quiet lesson about position. Earth does not sit in a specially designed chamber balanced between cosmic walls. It occupies a location shaped by ordinary structure formation. Elsewhere, other galaxies drift through sparser or denser surroundings according to the same laws. No observed pattern places Earth at a privileged geometric point within the large universe. The deepest maps show structure, not selection. When the eye of science rests on these scales, the familiar language of world, sky, and horizon loses its ordinary force. The meaningful boundaries are now hundreds of millions of light-years wide. The relevant contrasts are between rich flows of galaxies and thin cosmic deserts. In that setting, Earth is less than a speck. It is part of one small system buried inside one galaxy, itself no more than one occupant of a much larger crowded region, bordered by emptiness vast enough to swallow all ordinary measures. Superclusters and voids do not simply make the universe look large, they reveal a size difference so extreme that Earth slips almost entirely out of the picture. Beyond the widest superclusters and voids, astronomy narrows toward the particular large region that contains the Milky Way. This region is often described through the language of the local supercluster environment, especially the broad flow pattern called Laniakea and the nearby concentration centered on Virgo. These names refer to a gravitational landscape rather than a simple solid structure. Galaxies are not packed together in one glowing mass. They are spread across filaments, groups, and clusters, moving through expanding space while also responding to the pull of nearby concentrations of matter. Earth lies somewhere inside this setting, but only as part of a much smaller system buried deep within it. At this scale, the planet remains invisible. What becomes visible instead is the large terrain in which the Milky Way and many neighboring galaxies share a common cosmic neighborhood. Laniakea is the name given to a vast region defined by the way galaxies move. The idea does not rest only on where galaxies appear in the sky, but on their peculiar motions, which are motions relative to the general expansion of the universe. Space expands on large scales, carrying galaxies apart, yet gravity adds local departures from that overall drift. By measuring these departures, astronomers trace where galaxies seem to flow and which larger concentration of matter guides that flow. Laniakea describes one such basin of attraction, a broad region in which many galaxy groups and clusters move in patterns that indicate shared gravitational influence. It extends across roughly 500 million light-years and contains on the order of 100,000 galaxies. The boundaries are not sharp in the way a continent has a coastline. They are defined by motion, by the large-scale direction in which galaxies tend to drift through cosmic space. Within this broader setting lies the long-recognized Virgo supercluster region, named for the Virgo cluster, the nearest large galaxy cluster to the Milky Way. Earlier maps often treated the Virgo supercluster as the main supercluster that contains the Milky Way. More recent work places Virgo within the larger Laniakea flow pattern. The terminology changes as methods improve, but the underlying picture remains stable. The Milky Way exists in a local overdense region, not in isolation. It shares a broad gravitational environment with many thousands of other galaxies, and one of the most important nearby concentrations in that environment is the Virgo cluster. The Virgo cluster sits about 50 to 60 million light-years from the Milky Way and contains many hundreds, and likely more than 1,000, member galaxies depending on how the edges are counted. It is rich in hot gas and dark matter, and its total mass far exceeds the combined mass of its visible stars. Large elliptical galaxies dominate some of its central regions, while spiral and irregular galaxies are scattered through its wider extent. This cluster acts as a prominent local node in the surrounding cosmic structure. It does not pull everything directly inward in a simple straight path, because cosmic motion reflects many influences at once, but it marks one of the densest nearby sites in the larger home region of the Milky Way. Around Virgo and beyond it, galaxies are not arranged at random. They lie in sheets, filaments, and groups. The Milky Way belongs to one flattened arrangement often called the local sheet, a relatively thin structure of nearby galaxies sharing a similar broad placement in space. This sheet is itself part of larger connected forms that lead toward richer concentrations. The image that emerges is not of separate islands scattered without pattern, but of nested structure. A planet belongs to a star system belongs to a galaxy belongs to a group and sheet, and these belong to a supercluster scale environment shaped by mass and motion over hundreds of millions of light years. Earth exists at the deepest bottom of this nesting, so small that even the Milky Way must first shrink almost to nothing before the planetary scale disappears completely. The local supercluster region also reminds science that visible matter is only part of the whole. Galaxy motions do not match the pull expected from starlight alone. Dark matter contributes much of the mass that shapes these large flows. Hot gas between galaxies adds more. Some motions also reflect the influence of structures not easily seen behind the dense stars and dust of the Milky Way's own disk. For this reason, mapping the home supercluster is a gradual process. Telescopes observe galaxies in visible light, radio waves, infrared light, and X-rays, while distance measurements and motion studies slowly refine the larger map. The broad result is not complete certainty about every contour, but a steady strengthening of the same conclusion. The Milky Way moves within an extended gravitational province, and Earth is carried along inside that motion without any independent role. At this level, the scale of Earth becomes almost absurdly small. Even the solar system is irrelevant. The full orbit of the outer planets is negligible compared with the span between the Milky Way and Virgo. The width of the Milky Way itself, large enough to contain hundreds of billions of stars, is tiny against a regional structure hundreds of millions of light-years wide. Earth, resting on the edge of one ordinary star's habitable zone, cannot be pictured meaningfully on a map of Laniakea. The map would show flows, clusters, directions of attraction, and the relation of large structures to one another. It would not show planets. It would barely show individual stars. The entire human world falls far below the resolution that matters here. Yet the home supercluster is not a fixed machine. It changes slowly as galaxies move, groups interact, and the expansion of the universe continues. Some regions collapse more strongly under gravity, others drift apart. The language of superclusters therefore carries some uncertainty, because the largest structures are not always tightly bound objects with permanent edges. Observations indicate shared patterns of motion and shared environments, but not every named region is a single closed system. This uncertainty does not weaken the central fact, it sharpens it. The local cosmic neighborhood is not simple, and Earth is not positioned in some neat layered diagram with exact rigid borders. It is embedded in a dynamic structure whose true dimensions and motions vastly exceed ordinary imagination. Seen from the scale of Laniakea and Virgo, Earth is no longer merely small beside the universe as a whole. It is small even within its own broad neighborhood. The local supercluster region contains great streams of galaxies, massive concentrations of dark matter, hot gas spread through clusters, and distances so large that light itself requires tens of millions of years to move between major features. Against that setting, Earth is not a visible participant. It is a hidden point carried quietly within the Milky Way as the galaxy moves through one immense gravitational landscape among many in the observable cosmos. Inside the broad supercluster environment, The next inward region is the local group. This is the small collection of galaxies that contains the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and many smaller dwarf galaxies bound together by gravity. Compared with the scale of superclusters, the local group is modest. Compared with the scale of a single galaxy, it is immense. It spans roughly 10 million light-years from side to side, though its denser central population occupies a smaller region. Within this group, galaxies do not sit evenly spaced in a tidy pattern. They move through a shared gravitational field shaped mostly by the mass of the Milky Way and Andromeda, with dark matter contributing much of the total mass. Earth remains hidden deep inside one member of this group, so small that even the solar system cannot be meaningfully marked on a local group map. The local group contains more than just a few famous galaxies. Its brightest large spirals draw attention because they dominate the visible light. But most member galaxies are dwarfs. A dwarf galaxy is a much smaller galaxy with fewer stars and lower mass than a major spiral. Some are irregular in shape. Some are faint spheroidal systems with little gas and very old stars. Others still form stars slowly from remaining reservoirs of gas. Many orbit either the Milky Way or Andromeda as satellite galaxies. These satellites reveal that even a small galaxy group has internal layering. Large galaxies rule the mass and motion of the system, while smaller ones circle around them, sometimes stretched, disturbed, or partly stripped by gravitational interaction. The Milky Way and Andromeda stand as the two giants of the local group. Each is a large spiral galaxy containing hundreds of billions of stars, surrounded by dark matter halos extending far beyond the bright stellar disk. Triangulum, the third largest major member, is smaller, but still substantial. Around these principal galaxies are dozens of known dwarf companions, and additional faint dwarfs continue to be discovered as surveys deepen. The count is not fixed because the faintest galaxies are difficult to detect, especially when they contain few stars and lie against crowded backgrounds. Observations indicate that the full population of dwarf members is likely larger than the number already catalogued. Even so, the overall picture is clear. The local group is not a pair of large galaxies floating alone. It is a family of many systems linked by gravity across a region millions of light-years wide. Distances within the local group already dwarf ordinary imagination. Andromeda lies about 2.5 million light-years from the Milky Way. Light leaving Andromeda begins its journey long before human civilization arises in anything like its present form, and only now reaches Earth. Yet within the local group, Andromeda is near. It is one of the closest large galaxies. This reveals how swiftly scale grows in astronomy. A separation that would seem nearly infinite in human terms becomes local in galactic terms. Earth, with a diameter of just over 12,000 kilometers, shrinks beyond description in such a setting. Even the orbit of the outermost known dwarf satellites around the Milky Way can reach distances of hundreds of thousands of light-years, leaving the scale of planets completely behind. The local group is not static. The Milky Way and Andromeda move toward one another under their mutual gravity. Observations of their motion indicate that they are approaching, and on a timescale of several billion years they are expected to interact and eventually merge. This is not a sudden collision of stars like stones meeting in air. Galaxies are mostly space, and individual stars are so widely separated that direct stellar impacts remain unlikely. Instead, gravity reshapes the structure of both galaxies, drawing out streams of stars and gas, altering orbits, and gradually building a new larger galaxy from the combined system. This long future belongs to the local group itself, showing that even this smaller cosmic neighborhood evolves continuously over immense stretches of time. Dark matter is essential to understanding why the group holds together. The visible stars and gas do not provide enough mass by themselves to account for the observed motions of galaxies within the group. The unseen component, inferred through gravitational effects, forms extensive halos around the major galaxies and contributes strongly to the group's overall binding structure. Without this invisible mass, the local group would not behave as it does. This is another reminder that the visible universe is not the full physical one. Even in the relatively nearby cosmic neighborhood, much of the mass that governs motion does not shine. The local group also shows that scale can be intimate and enormous at once. On the one hand, it is a very small region compared with superclusters and the full cosmic web. On the other hand, it contains distances so vast that light itself requires millions of years to cross from one large member to another. The human world occupies a thin surface on one small planet inside one star system inside one galaxy within this group. No sense of daily life, national map, or planetary horizon can survive unchanged once this scale is absorbed. Earth is not the center of the local group, nor even close to any meaningful central point. It accompanies the Milky Way through the group's shared gravitational life as a tiny passenger on a star-bound orbit. The local group is also shaped by past encounters. Some dwarf galaxies show signs of tidal disruption, meaning they're pulled apart by the gravity of larger companions. Streams of stars arc around the Milky Way, evidence that smaller galaxies have been absorbed over time. Andromeda shows similar signs of a history built partly through merger and capture. The group is therefore not only a collection but also a process. Galaxies enter, interact, lose material, merge, and change. Earth exists in a galaxy that has grown through such events, though none of those ancient transformations leaves a visible mark on the scale of a human life. Seen from the level of the local group, Earth becomes smaller in a more personal way than before. The earlier sections place it against abstract immensity, against horizons, webs, voids, and supercluster flows. Here, the comparison narrows to neighboring galaxies, yet the reduction remains overwhelming. Even the nearest large galactic neighbor lies millions of light-years away. The local group is the Milky Way's immediate community, and still Earth cannot appear within it as anything more than an unthinkably tiny hidden world, carried within one spiral member of a quiet but immense galactic family. Inside the local group, the next inward region is the outer halo of the Milky Way. This is the broad, faint realm that surrounds the bright disk of the galaxy. The word halo here means the wide envelope around the main visible body, not a shining ring. Much of it is nearly empty by ordinary standards. Its stars are sparse, its gas is thin and often very hot. Its most important mass, dark matter, cannot be seen directly at all. Yet this outer region extends far beyond the familiar band of the Milky Way visible in the night sky, and it contains crucial evidence about how the galaxy forms and grows. Earth lies deep inside the bright inner parts of the Milky Way, but at halo scale even the entire stellar disk becomes only the central core of a much larger system. The visible night band of the Milky Way gives a misleading first impression. It suggests that the galaxy is mainly a flat concentration of stars and dust. That is true for the bright portion most easily seen, but it is not the whole galaxy. Surrounding the disk is a much more diffuse stellar halo, made of old stars spread through a broad, roughly spherical region. These stars are far less crowded than those in the disk. Their orbits are often tilted, elongated, and varied in direction, unlike the more orderly motion of many disk stars around the galactic center. This difference in motion reveals that the halo preserves a different history. It is not simply an outer continuation of the bright disk. It is a separate component, built in part from the remains of smaller systems absorbed over long spans of time. Among the most striking inhabitants of the halo are globular clusters. A globular cluster is a dense, rounded swarm of very old stars held together by gravity. The Milky Way contains roughly 150 known globular clusters, with a few more possible members still under study. These clusters orbit far above and below the galactic plane. Many are ancient, with ages close to the age of the galaxy itself. Their stars tend to be poor in heavy elements compared with younger stars in the disk, which suggests that they form early in cosmic history. In the halo, these clusters appear like distant markers of a vast outer volume, though even their combined light traces only a small part of the region's full mass. The stellar halo itself is not smooth. Surveys reveal streams and shells of stars stretched across the outskirts of the Milky Way. These are the remnants of dwarf galaxies and star clusters torn apart by tidal forces, meaning the varying pull of gravity across their size. When a smaller system falls into the Milky Way, its stars can be drawn out into long ribbons that continue to orbit for immense periods. Such streams show that the halo is a record of assembly. It carries the marks of accretion, the process by which a larger galaxy grows by taking in smaller companions. Its sparse stars preserve clues to past mergers that the brighter disk may later blur. Far beyond the visible stars lies an even more important part of the halo: the dark matter halo. Dark matter is the invisible mass inferred from gravity. In the Milky Way, it dominates the galaxy's total mass. The bright stars, glowing gas, dust clouds, planets, and stellar remnants make up only a minority of the full mass. The dark halo extends much farther than the luminous disk and likely reaches out several 100,000 light-years from the galactic center. Its exact boundary remains uncertain because dark matter does not present a sharp outer wall. Its density gradually falls with distance, blending into the wider environment of the local group. Even with that uncertainty, observations leave little doubt that the Milky Way is embedded in a massive dark envelope far larger than the visible galaxy alone. This unseen halo shapes the motions of stars and satellite galaxies. It helps explain why outer parts of the galaxy orbit as they do, and why dwarf companions remain gravitationally associated with the Milky Way across large distances. Without dark matter, the visible mass would not be enough to account for the observed speeds. Earth, which seems substantial from its own surface, disappears entirely in this comparison. The whole planet is less than nothing at halo scale, and even the Sun is only one ordinary star deep inside the central luminous region of a galaxy whose most massive component cannot be seen. The halo also contains gas, much of it in the circumgalactic medium. This term refers to the diffuse gas surrounding a galaxy outside its main star-filled disk, but still within its wider gravitational reach. Around the Milky Way, much of this gas is hot enough to emit or absorb in X-rays and ultraviolet light rather than visible light. It is thin, difficult to detect, and spread across a large volume. Yet it matters greatly. It stores part of the galaxy's ordinary matter and forms part of the reservoir from which later galactic processes draw. Some of this gas likely enters from intergalactic space. Some has been pushed outward by energetic events inside the galaxy, such as stellar winds and supernova explosions. The halo is therefore not empty background. It is a broad exchange region between the galaxy and its surroundings. The outer halo changes the meaning of the Milky Way's size. If size refers only to the bright disk, the galaxy has one familiar scale. If size includes the globular cluster system, the stellar halo, the hot gas, and especially the dark matter envelope, the galaxy becomes far larger. The bright disk is then only the inner luminous concentration inside a much wider domain. Common images of the Milky Way often highlight the shining spiral and stop there. The fuller physical system extends vastly beyond that light. The halo remains thinly populated compared with the disk, but its thinness is part of its importance. It allows ancient structures to survive. It preserves the tracks of smaller galaxies taken apart long ago. It holds old clusters whose stars form near the beginning of galactic history. It contains the invisible mass that governs much of the galaxy's overall gravity. Seen from the scale of the Milky Way halo, Earth is a minute object buried in the dense inner light of one galaxy, whose true reach spreads outward through sparse stars, hot gas, and an enormous unseen halo that surrounds the Milky Way like a vast and quiet gravitational sea. Inside the wide halo of the Milky Way lies the galaxy's main stellar disk, the bright flattened region that gives the Milky Way much of its visible form. This disk is the broad galactic plane where most of the galaxy's stars, much of its gas, and most of its dust are concentrated. It is not a solid plate and not a sharply bounded object. It is a rotating structure of many components layered through one another, with older stars, younger stars, cold gas clouds, warm gas, dark dust lanes, and the remains of earlier generations of stars all sharing the same vast rotating system. Seen from far outside, the disk gives the Milky Way the appearance of a barred spiral galaxy, with curving arms embedded in a flattened luminous body. Seen from within, where Earth resides, the disk appears as the pale river of light across the night sky. At this scale, Earth is not merely small beside the galaxy. It is hidden so deeply within one thin interior layer that the whole planet vanishes into the background of galactic structure. The disk extends roughly 100,000 light-years across, though its exact visible edge depends on what is being measured. Some stars and gas stretch farther, and the outer parts thin gradually rather than ending in a sharp rim. Its thickness is small compared with its width. The thin disk, where many younger stars and much of the gas reside, is only a small fraction as thick as it is wide. There is also a thicker disk made of older stars whose orbits carry them somewhat farther above and below the galactic plane. Together, these components form the main luminous body of the Milky Way. This flattened shape arises because matter settling into rotation around the galactic center tends to spread into a disk, much as particles in a rotating system gradually occupy a preferred plane. Rotation governs the disk. Stars and gas orbit the galactic center, though not all at the same speed in simple solid fashion. The Milky Way does not spin like a rigid wheel. Instead, material at different distances from the center circles with different orbital periods. The Sun, for example, takes about 230 million years to complete one orbit around the center. This long galactic year reveals the scale of the disk more clearly than any local measure can. During all of recorded human history, the solar system moves only a tiny fraction of the way around the galaxy. Earth's yearly orbit around the Sun, so central to ordinary life, becomes almost negligible inside this much slower and larger rotation. The disk contains a tremendous range of stellar environments. Some regions are filled with old stars that have orbited the galaxy for billions of years. Other regions contain cold molecular clouds, dense accumulations of gas and dust where new stars form. A molecular cloud is a cold interstellar cloud in which atoms combine into molecules, especially molecular hydrogen, though that hydrogen is difficult to observe directly. In the denser parts of such clouds, gravity can overcome internal pressure and begin the process of star formation. Young bright stars then emerge, often in loose groups, and their light, winds, and later explosions help reshape the surrounding gas. The disk therefore contains not only stars already formed but also the raw material and active processes that continue building new generations. Dust is a small part of the disk by mass, but it has a large visual effect. Fine grains of carbon-rich and silicate material drift through interstellar space and absorb visible light. Because of this dust, distant parts of the Milky Way disk are partly hidden from view at visible wavelengths. Dark lanes cut through the glowing band of the galaxy. In infrared light and radio waves, more of the hidden structure becomes visible. The need to observe through many wavelengths is itself evidence of the disk's complexity. The Milky Way is not a smooth luminous sheet. It is layered, patchy, clouded, and dynamic. The spiral pattern belongs mainly to the disk as well. The Milky Way has spiral arms, though the exact details are harder to map from inside than they are in external galaxies viewed from afar. These arms are not fixed, solid tubes of stars moving together unchanged. They are better understood as patterns of enhanced density, regions where gas and stars crowd somewhat more strongly than in surrounding areas. As gas enters these denser regions, it can compress and help trigger star formation. Bright young stars then help outline the arms. This makes the disk both structured and changing. Its large pattern persists across long spans, while individual stars move in and out of local features over time. The disk also contains most of the galaxy's ordinary luminous mass. Stars dominate what is seen directly, but gas and dust provide the medium from which later stars form and through which energy and heavy elements are redistributed. Heavy elements, meaning chemical elements heavier than hydrogen and helium, are produced in stars and return to the interstellar medium through winds and explosions. The disk is therefore a long-lived circulation system. Matter forms stars, stars transform matter, and some of that matter returns to the disk to participate again in later cycles. Earth, made from heavy elements forged in earlier stars, belongs physically to this history. Yet as an object it remains inconceivably small beside the structure that makes such material available. The sense of place changes again at the scale of the disk. The Milky Way is no longer only an abstract galaxy among others. It becomes a broad inhabited stellar system in which position, motion, gas, dust, and light define a real environment. Yet Earth gains no central status from being inside it. The galaxy does not arrange itself around the planet. The disk does not notice the existence of one world orbiting one star. Even the solar system is a tiny local feature in a disk containing hundreds of billions of stars and enormous interstellar clouds spread across tens of thousands of light years. Seen at this level, Earth disappears into a rotating galactic plane. The widths involved are so great, and the stellar population so vast, that the planet cannot carry any visible or structural importance. The Milky Way disk is a flattened ocean of stars, gas, dust, and motion, extending across 100,000 light-years and turning slowly around its hidden center. Against that immense rotating body, Earth is a minute and unseen world embedded far within the bright galactic plane. Within the broad disk of the Milky Way, the Sun occupies a modest neighborhood inside a small spiral feature often called the Orion Arm, or Orion Spur. This region is not one of the galaxy's largest primary arms. It is a minor structure lying between the larger Sagittarius Arm and Perseus Arm. The solar system travels within this smaller lane of stars. Gas, and dust at a distance of about 26,000 light-years from the galactic center. That distance alone is enough to place Earth far from any central role. Yet the Orion Arm brings the scale inward in a quieter way. It is the local galactic district around the Sun, the surrounding part of the Milky Way where nearby stars, interstellar clouds, and faint star-forming regions define the setting through which the solar system moves. The word arm can suggest a sharply outlined branch, but spiral arms in galaxies are not rigid tubes. They are broad regions where stars and gas are somewhat more concentrated than average. The Orion Arm is better understood as a local segment or spur, a smaller stretch of enhanced structure within the disk. It contains young stars, older stars, nebulae, dust clouds, and open star clusters. An open cluster is a loose group of stars that forms together from the same cloud and remains associated for a time before the galaxy's motions gradually disperse it. Such groups are common signposts of recent star formation in the local galactic environment. The Sun does not sit in a dense glowing center of this region. Its neighborhood is relatively ordinary by galactic standards. Nearby stars are separated by distances so large that even the closest one beyond the Sun, Proxima Centauri, lies more than 4 light-years away. Other familiar nearby stars, such as the Alpha Centauri pair, Barnard's star, Sirius, and Epsilon Eridani, belong to the same broad local stellar surroundings, though each follows its own orbit through the galaxy. These stars are not arranged in a neat pattern around the Sun. They drift through the local region with different speeds and directions, shaped by the long orbital life of the galactic disk. Most of the local volume is still empty space. Even inside a spiral feature, stars do not crowd together the way lights crowd a city. The average separation between stars is vast. A star system can travel for long spans through the galaxy without coming near another star in any immediate sense. This emptiness is important to scale. The Orion Arm feels local only because it is smaller than the whole galaxy, not because it is compact. Earth remains tiny even here, because the Sun's nearby stellar neighborhood already extends across distances that light needs years to cross, and spacecraft would need immense spans to traverse. Between the stars lies the interstellar medium, the thin gas and dust that fill the spaces of the galaxy. In the Orion Arm, this medium is varied. Some regions hold cold, dense clouds where stars are beginning to form. Others contain warmer, thinner gas shaped by older stellar activity. The Sun currently lies within a small region of thin, warm interstellar gas, itself inside a larger cavity known as the local bubble. This bubble is a region of unusually low-density hot gas extending for hundreds of light-years, likely shaped by supernova explosions from long ago. A supernova is the violent death of a massive star or the explosive destruction of a white dwarf under particular conditions. Such events send energy and material into surrounding space, carving cavities and compressing nearby clouds. The local neighborhood, therefore, is not static. It bears the marks of older stellar events that change the texture of the interstellar environment. Along the Orion Arm lie well-known star-forming clouds and nebulae. The Orion Molecular Cloud Complex is one of the nearest large stellar nurseries, though still far beyond any direct human reach. In such clouds, cold gas gathers into denser clumps, and gravity slowly draws those clumps inward until new stars ignite. Bright young stars then light the surrounding gas, making nebulae visible across the arm. Other nearby structures, such as the Taurus Molecular Cloud and the Perseus star-forming region, reveal that the local galactic neighborhood includes both quiet older stars and places where new stellar generations continue to emerge. The Sun happens to lie near such regions, but not inside one. Its present local setting is comparatively calm. This calm does not mean isolation. The solar system moves through the Orion Arm as the Milky Way rotates. Nearby stars move as well, some gradually approaching, others receding, all sharing the broad circulation of the galactic disk while keeping their own local motions. Over millions of years, the nearest stellar neighborhood changes. Constellations slowly alter. Close passages remain rare, but the local sky is not permanent. The sun is one traveler among many in a moving galactic community. The Orion Arm also contains a long history of chemical enrichment. Earlier generations of stars form from simple gas, live, and return heavier elements to the interstellar medium. Later stars and planets then form from matter already enriched by those earlier lives. The Sun and Earth belong to this continuing process, but the process itself belongs to the arm and the disk, not to any special quality of one planet. Earth is physically made from galactic material shaped through repeated stellar cycles, yet as an object it remains almost nothing in size compared with even the immediate local neighborhood from which that material comes. Seen at this scale, the Milky Way stops feeling like a single distant object and becomes a structured local environment. The Orion Arm contains stellar nurseries, drifting field stars, open clusters, thin gas, dust, old supernova-shaped cavities, and wide regions of relative quiet. It is the Sun's galactic address, but only in a broad and humble sense. The solar system occupies one small location within one modest spiral feature of one ordinary disk galaxy. Earth does not grow larger because the scale narrows. It only becomes more precisely placed. It is a tiny world orbiting one star in the Orion Arm, surrounded by nearby stars separated by light years, embedded in thin interstellar gas, and carried through a minor spiral structure far from the galactic center. Even in this local galactic neighborhood, where the distances are smaller than those between galaxies and clusters, Earth remains minute beyond all ordinary comparison, hidden inside one small system moving quietly through the Sun's corner of the Milky Way. Beyond the Sun's local galactic neighborhood, the next inward region is the far outer frontier of the solar system. This frontier is not a sharp shell surrounding the planets. It is a broad and layered outer domain where sunlight grows weak. Orbital periods become enormously long, and the Sun's influence is expressed less through warmth or brightness than through gravity. In this region, the familiar inner picture of the solar system gives way to a sparse realm of ice-rich bodies, thin streams of particles, and boundaries defined more by gradual change than by solid edges. Earth belongs to this same solar system, yet from the scale of its outer frontier the planet is only a tiny inner member hidden close to the Sun compared with the enormous distances that reach outward into the dark. One important part of this frontier is the Kuiper Belt. The Kuiper Belt is a broad region beyond Neptune containing many icy bodies left over from the early formation of the solar system. It is not a dense ring of objects packed side by side. It is a wide, thin population of frozen remnants spread through a large volume of space. These bodies, called trans-Neptunian objects, include dwarf planets such as Pluto, Haumea, and Makemake, along with many smaller worlds of rock and ice. Some move in relatively regular paths. Others follow more stretched and tilted orbits shaped by long gravitational interactions. The Kuiper Belt begins beyond the orbit of Neptune and extends outward for many billions of kilometers, though its population thins and changes with distance. Sunlight in the Kuiper Belt is faint. The Sun still dominates gravity there, but its visible brightness has diminished so much that day in such a region would resemble a very bright star rather than the blazing sun seen from Earth. Temperatures are extremely low, and volatile substances that would evaporate quickly near Earth can remain frozen for immense spans. In this dim outer region, many objects preserve materials from early solar system history. They are valuable to astronomy because they carry chemical and structural clues from the time when the planets were forming. Yet as places they are quiet, cold, and widely separated. The emptiness between them remains one of the defining facts of the outer solar system. Beyond the more stable part of the Kuiper belt lies the scattered disk. This is a population of icy bodies on more elongated and often more tilted orbits, likely shaped by strong gravitational disturbance in the early history of the solar system. A scattered object can travel very far from the Sun and then return inward over long intervals. These orbits reveal that the outer frontier is not a neat architectural zone with perfectly layered rings. It is a record of dynamical history, meaning a history shaped by motion and gravitational interaction. Bodies in the scattered disk preserve evidence that the young solar system was not static. It was a place where migrating masses and repeated gravitational encounters changed the arrangement of smaller icy worlds. Still farther outward lies the region associated with the Oort cloud. The Oort cloud remains inferred rather than directly observed in full. Observations of long-period comets indicate that the solar system is surrounded by a vast distant reservoir of icy bodies, extending perhaps thousands to tens of thousands of astronomical units from the Sun, and possibly farther. An astronomical unit is the average distance between Earth and the Sun. At such distances, the Sun's gravity still defines the basic bond, but the hold becomes weak enough that passing stars and the tidal pull of the Milky Way can disturb these distant objects. The Oort cloud, if described as a cloud, is not a compact glowing swarm. It is a huge, sparse shell-like distribution of icy bodies surrounding the planetary region at tremendous remove. It marks one of the furthest known reaches of the Sun's gravitational domain. Comets offer brief evidence of this remote storehouse. When some icy bodies are perturbed inward, they begin long falls toward the inner solar system. As they approach the Sun, heat releases gas and dust, producing the bright coma and tail that make comets visible. Those tails do not point behind the comet simply because it moves forward. They are shaped by sunlight and the solar wind, the continuous flow of charged particles from the Sun. In the outer frontier, before such bodies descend inward, they remain dark, frozen objects moving through deep cold over periods far longer than human civilizations endure. The solar system's frontier is not defined only by orbiting icy bodies. It also includes the outer reach of the Sun's outflow. The heliosphere is the broad bubble-like region created by the solar wind as it pushes outward against the interstellar medium. This region extends far beyond the planets. Its exact shape changes with solar conditions and with the surrounding galactic environment, but observations from spacecraft show that it reaches far into the outer solar system before giving way to interstellar space. The heliopause is the boundary where the outward pressure of the solar wind is balanced by the surrounding interstellar medium. It is not a wall of solid matter, but a transition. Beyond it, the Sun's wind no longer dominates the local particle environment, though the Sun's gravity continues much farther out. This distinction matters. The heliosphere marks the Sun's space weather reach, while the Oort region marks the probable extent of its distant gravitational family. The two are not the same boundary. One concerns flowing particles and magnetic influence. The other concerns long-term orbital control over icy bodies. Together they show that the solar system fades outward by stages. Light weakens, heat diminishes, planet-like worlds become rare and small. The Sun's wind yields to interstellar conditions. Gravity alone continues to hold distant remnants in enormous dark orbits. At this scale, Earth becomes profoundly inward and profoundly small. The planet orbits at 1 astronomical unit from the Sun, a distance that seems large in everyday thought. Yet against the Kuiper belt, the scattered disk, the heliosphere, and the inferred Oort cloud, that orbit lies close to the centre. Earth is not near the edge of the solar system, it is deep within it, the inhabited world of oceans, air, and continents belongs to a narrow inner zone that occupies only a minute fraction of the Sun's full domain. Seen from the outer solar frontier, the solar system is not mainly a place of bright planets. It is a vast fading sphere of influence with icy populations at its edge, dim sunlight stretched thin across remote orbits, and a solar presence that weakens gradually into the wider galaxy. Earth remains part of this system, but it is reduced to one small inner world circling close to the Sun, while the true extent of the solar system reaches outward into distances so large and so cold that the familiar scale of the human world disappears almost completely. Inside the far outer frontier of the solar system lies the realm of the giant planets. This is the broad region shaped by Jupiter, Saturn, Uranus, and Neptune, the 4 large outer planets that contain most of the planetary mass orbiting the Sun. Their orbits span a wide range of distance, and the space between them is immense. These worlds differ in composition and appearance, yet together they define the large outer architecture of the solar system. They show that even after the scale narrows from galactic and interstellar distances to the orbiting family of one star, Earth remains physically small and spatially tucked far inward, compared with the broad lanes occupied by the giants. Jupiter is the largest planet in the solar system. Its diameter is about 143,000 kilometers, more than 11 times the diameter of Earth. Its mass is greater than that of all the other planets combined. It is made mostly of hydrogen and helium, the light elements that also dominate the Sun, though Jupiter never becomes hot and dense enough in its centre to ignite as a star. Beneath its cloud tops, pressure rises steadily through layers of gas and fluid until matter enters forms not found at Earth's surface. The visible bands and storms in Jupiter's atmosphere reveal a world of rapid rotation, strong winds, and deep meteorology. Seen beside Jupiter, Earth is not a small equal. It is a minor rocky globe beside a planetary giant large enough to contain more than 1,000 Earth-sized volumes. Saturn follows farther from the Sun, and though it is less massive than Jupiter, it is still a vast world. Its diameter is about 120,000 kilometers. It is known most clearly by its ring system, but the rings are only one part of the planet's scale. Saturn, too, is made mostly of hydrogen and helium, with a deep-layered interior and an atmosphere marked by belts, storms, and seasonal changes. Its average density is lower than that of water, though this fact belongs to a mathematical comparison rather than any practical physical setting. Like Jupiter, Saturn occupies a broad orbital path that lies far beyond the warm brightness familiar at Earth. Sunlight there is weaker, the years are longer, and the planet moves through a much wider circumference around the Sun. Uranus and Neptune lie farther still. These two are often grouped as ice giants because, compared with Jupiter and Saturn, they contain a greater proportion of substances such as water, ammonia, and methane in deeper layers, though not in the simple frozen form suggested by the everyday word ice. Uranus has a diameter about 4 times that of Earth and is notable for its extreme axial tilt, which causes unusual long seasonal patterns. Neptune is slightly smaller in diameter than Uranus but more massive, with powerful winds in its atmosphere and a deep blue colour produced in part by methane absorption of red light. Both planets orbit at distances where sunlight has grown faint, yet they remain fully part of the Sun's ordered system, circling on timescales far longer than any human life. The spacing of these planets is itself one of the main lessons of scale. Jupiter lies about 5 astronomical units from the Sun, Saturn about 9.5, Uranus about 19, and Neptune about 30. An astronomical unit is the average distance between Earth and the Sun. These numbers mean that the outer solar system expands quickly in both physical distance and orbital period. A year on Jupiter lasts nearly 12 Earth years. A year on Saturn lasts nearly 29 Earth years. Uranus requires about 84 Earth years to circle the Sun once, and Neptune about 165 Earth years. These long orbital times reveal that the giant planet region is not simply a list of large worlds. It is a wide and slowly turning outer framework. Between the planets there is no crowded parade of bodies. The space is mostly emptiness, crossed by sunlight, solar wind, magnetic fields, dust, and occasional smaller bodies. The emptiness does not lessen the importance of the region. It defines it. The great separation between the giant planets shows how large the solar system already is, long before its distant frontier is reached. Earth's orbit, so meaningful in human experience, occupies only one inner interval within a much larger system whose outer planetary lanes stretch across billions of kilometers. Each giant planet also carries its own system of moons, rings, and magnetic influence. Jupiter has dozens of known moons, including the 4 large Galilean moons, worlds substantial enough to be planetary in character, though bound to a larger planet. Saturn likewise hosts a rich family of moons, among them Titan, wrapped in a thick atmosphere, and Enceladus, with plumes of water-rich material erupting from its icy surface. Uranus and Neptune also possess moon systems and rings, though less visually dominant than Saturn's. These satellite families reveal that the giant planet realm contains nested systems within systems. A planet orbits the Sun, while moons orbit the planet, and rings circle still closer in complex gravitational relation. Earth's single large moon gives one example of such structure on a smaller scale. But beside the outer planets, the scale of these systems becomes far greater and more varied. The giant planets also help shape the solar system dynamically. Their gravity affects small bodies, alters orbital resonances, and has influenced the long history of planetary arrangement. Jupiter in particular exerts a powerful gravitational role because of its mass. Orbital resonances, meaning repeated gravitational relationships tied to simple ratios of orbital periods, can create regions of stability or instability for smaller bodies. The outer system is therefore not only wide, it is organized by recurring gravitational patterns centered on the great planets. Seen from this region, Earth becomes small in 2 distinct ways. It is physically much smaller than the giants, especially Jupiter and Saturn. It is also located far inward, inside the broad outer arrangement that these planets define. The contrast is humbling because the giant planet realm is still only one portion of the solar system, yet within that portion alone the familiar world of land, ocean, air, and life is reduced to one minor rocky planet compared with immense gaseous and icy bodies following long, slow orbits around the Sun. The realm of the giant planets reveals that the solar system is not built to human scale even in its planetary core. It is a system of large masses, wide separations, deep time, and nested gravitational order. Jupiter, Saturn, Uranus, and Neptune occupy the outer lanes like vast anchors of the Sun's planetary family. Against their size and their distance, Earth is both small in body and inward in place, a tiny rocky world set well inside the wide outer architecture of the giant planets. Inside the broad outer realm of the giant planets lies the inner planet region, the compact zone occupied by Mercury, Venus, Earth, and Mars. These four worlds differ sharply from the giants beyond them. They are smaller, denser, and made largely of rock and metal rather than deep envelopes of hydrogen and helium. Their surfaces, or in the case of Venus, their hidden rocky ground beneath a thick atmosphere, belong to the solid inner architecture of the solar system. Their orbits lie much closer together than those of the outer planets, and this tighter spacing can make the inner solar system seem almost compact. Yet even here the distances remain vast by ordinary standards. Earth appears larger only because the scale has narrowed. In truth, it remains one small rocky member of a four-planet region whose proportions already surpass all familiar human measures. Mercury is the innermost planet. It is the smallest of the four rocky planets, and the nearest to the Sun. Its surface is heavily cratered, with wide plains, ancient impact scars, steep cliffs formed as the planet cools and contracts, and a large metallic core relative to its size. Mercury has almost no substantial atmosphere in the everyday sense. Instead, it possesses a very thin exosphere, a sparse cloud of atoms so diffuse that it behaves nothing like the air around Earth. Days and nights there differ strongly in temperature because without a thick atmosphere there is little to redistribute heat. Mercury circles the Sun in only 88 Earth days, moving swiftly along the smallest planetary path in the solar system. Venus follows outward and is often called Earth's sister planet because its size is broadly similar to Earth's, yet the resemblance ends quickly. Venus is wrapped in an extremely dense atmosphere dominated by carbon dioxide, with clouds of sulfuric acid and a surface pressure crushing far greater than that at sea level on Earth. Its surface temperature is high enough to melt lead, not because Venus lies vastly closer to the Sun than Earth, but because its thick atmosphere traps heat through a powerful greenhouse effect. The planet rotates slowly and in the opposite direction from most planets, a retrograde spin whose exact early causes remain uncertain. Observations strongly constrain the present state of Venus, while aspects of its deeper history remain under study. Venus shows that in the inner planet region, worlds of similar size can diverge into radically different environments. Earth occupies the next orbit outward. It is the largest of the four rocky planets, though only slightly larger than Venus in diameter. Its atmosphere, surface water, active geology, and moderate temperatures make it unusual among the inner planets. But in the architecture of the region it remains one member among four. Its orbit lies between the hostile furnace of Venus and the colder, thinner-aired desert of Mars. The position of Earth in this sequence can feel central from a human point of view, but the geometry of the region gives it no privileged physical scale. It is one rocky body travelling on one orbital track in a compact planetary zone. Mars forms the outer edge of the inner planet set. It is smaller than Earth and Venus, with a thin atmosphere, polar ice caps, extinct giant volcanoes, long canyon systems, and abundant evidence that liquid water once flowed across its surface in the distant past. Today, its cold, dry conditions differ sharply from Earth's. Yet it still belongs clearly to the same terrestrial class of rocky worlds. Its red appearance comes largely from iron-rich minerals altered by oxidation. Mars takes about 687 Earth days to complete an orbit. Marking the outer margin of the inner planetary region before the spacing widens and the character of the solar system changes toward the giant planets, and the main asteroid belt beyond. The inner planets share several broad properties. All have solid surfaces shaped by impacts, volcanism, tectonic forces, or ancient crustal change. All are denser than the giant planets because heavy materials such as silicates and metals dominate their composition. All occupy relatively short orbital paths compared with the huge lanes farther out, yet the similarities do not erase their differences. Mercury is airless and extreme in day-night contrast. Venus is hot, pressurized, and cloud-wrapped. Earth is ocean-bearing and geologically active. Mars is cold, dusty, and thinly blanketed by gas. The inner region is therefore not a repetition of one design, but a small family of distinct rocky outcomes. Its compactness, however, remains one of its most important lessons in scale. The 4 inner planets fit within a relatively narrow span compared with the giant planets. Their orbits cluster near the Sun. From Mercury to Mars, the distances are small by solar system standards, yet still so large that travel between them remains difficult and slow by human technology. Even the distance between Earth and its nearest planetary neighbours changes greatly depending on orbital positions. Planets do not sit on a line waiting at fixed intervals. They move continuously, so their separation grows and shrinks over time as each follows its own path. This motion reveals another quiet truth about scale. The inner solar system is not a set of points on a textbook page. It is a moving region of curved orbits, changing alignments, and long repeating patterns. Mercury circles quickly. Venus follows more slowly. Earth completes its year. Mars moves on a broader track. These different orbital periods mean that planetary geometry is always shifting. The region is compact compared with the outer solar system, but it is still spacious enough that planets spend most of their time very far from one another. Earth's size also changes in feeling when set beside its rocky neighbours. It is not uniquely large, nor is it tiny like Mercury. It sits within a narrow range of terrestrial planet sizes. This makes the Earth seem less singular as an object and more like one example of rocky planetary formation. Its continents, seas, air, and living surface are extraordinary in known biology, but its body as a planet is still modest, even within the inner region, where worlds are smaller than Jupiter and Saturn by far. Earth does not dominate by mass or by spatial extent. It is a mid-sized terrestrial planet in a small interior band. Seen from the scale of the inner planet region, Earth becomes part of a compact but still immense arrangement of solid worlds. Mercury, Venus, Earth, and Mars circle on neighbouring tracks inside the broad solar system, each carrying a different surface story, each shaped by the same early planetary process yet altered by its own history. The region feels near only in comparison with what lies beyond it. In absolute terms, it is still vast, and Earth remains one small rocky world occupying a narrow orbital lane among a handful of inner planets. At the centre of the planetary system lies the Sun, the dominant body of the solar system, and the object that determines nearly every large-scale condition under which Earth moves. The Sun contains about 99.8% of the solar system's mass. This single fact changes the meaning of scale more than any comparison among planets can do. Earth may seem large from its own surface, but beside the Sun it becomes a small secondary body, held in motion by the gravity of a star so massive that all the planets together account for only a tiny remainder. The solar system is therefore not best understood as a family of equal worlds. It is a star-centered system, with Earth following one particular path within the Sun's overwhelming gravitational and radiative reach. The Sun is a main sequence star, meaning a star that spends the long, stable part of its life fusing hydrogen into helium in its core. In the Sun's center, pressure and temperature are high enough for nuclear fusion to occur continuously. This process converts a small fraction of mass into energy, and that energy slowly works its way outward before streaming into space as sunlight and other radiation. The Sun does not burn like wood or flame on Earth. Its power comes from fusion, the joining of lighter atomic nuclei into heavier ones. That steady release of energy sustains the light and heat reaching Earth, while the Sun's mass sustains the orbit that keeps Earth bound. In size, the contrast is immediate. The Sun's diameter is about 1,390,000 kilometers, more than 100 times the diameter of Earth. More than 1 million Earth-sized volumes could fit inside the Sun, though that comparison simplifies the real difference because the Sun is a sphere of hot plasma, not a solid container. Plasma is matter in which electrons are no longer bound to atomic nuclei, creating an electrically conducting state. Most of the visible universe is made of plasma, and the Sun is one nearby example on a grand scale. Earth, by contrast, is a small, dense, rocky planet with a thin outer atmosphere and a cool solid surface. One is a star, the other is a minor companion body orbiting at a distance that is safe for liquid water to persist. That orbital distance averages 1 astronomical unit, about 150 million kilometers. This number is large in any human measure, yet it is not large compared with the size of the solar system as a whole. Earth circles the Sun once each year on an orbit that is very close to circular, though not perfectly so. The path is an ellipse, a slightly stretched circle, with the Sun near its center. Because the orbit is only mildly elliptical, the change in Earth's distance from the Sun across the year is relatively small compared with the total distance involved. Seasons do not arise chiefly from that small distance change. They arise because Earth's axis is tilted relative to its orbital plane. Yet even while that tilt shapes climate and daylight, the deeper scale fact remains the same. Earth's yearly motion is the motion of a small planet tracing one modest inner path around a star that governs the system. The speed of that motion is also revealing. Earth moves around the Sun at about 30 kilometers per second. This is fast by any planetary standard familiar to everyday life. Yet no direct sensation accompanies it on the surface because Earth and its atmosphere move together in the same orbital flow. The planet is not suspended motionless in space. It continuously falls around the Sun. Orbit is the balance between forward motion and gravitational attraction, a perpetual falling that curves into a closed path. In this sense, Earth does not stand apart from solar influence. It is always under it, always moving within it, always defined by it. The Sun is not only a source of gravity, it is also the source of nearly all the energy that drives Earth's surface environment. Sunlight warms land and oceans, powers atmospheric circulation, sustains photosynthesis, and shapes the daily alternation of light and dark through Earth's rotation. The energy received at Earth is only a tiny fraction of the Sun's total output, because the radiation spreads outward in all directions. By the time it reaches Earth's orbit, it crosses a sphere of enormous area. Earth intercepts only a small portion of that flow. Even so, that small intercepted share is enough to maintain the surface conditions under which life persists. Scale appears here in a subtle form. The Sun is so powerful that even a minute fraction of its radiated energy can sustain an active planetary climate on a world far away. The Sun also sends out the solar wind, a continuous stream of charged particles flowing through the solar system. At Earth's distance, This flow interacts with Earth's magnetic field and upper atmosphere, helping produce auroras near the poles and contributing to what is called space weather. The Sun therefore affects Earth not only through light and gravity, but also through particles and magnetic activity. Solar flares and coronal mass ejections can disturb this environment, though Earth's atmosphere and magnetic field provide important protection at the surface. This ongoing connection further emphasizes that Earth is not an isolated globe drifting on its own terms. It is embedded in the physical reach of its star. The scale contrast between Sun and Earth becomes even clearer when density and composition are considered. Earth is made mostly of rock and metal, with a layered interior and a solid outer shell broken into tectonic plates. The Sun is mostly hydrogen and helium, held together in a sphere by its own gravity and structured by deep pressure, heat, and plasma motion. Earth's mass is tiny compared with the Sun's, about 330,000 times smaller. This difference explains why Earth does not pull the Sun around in any everyday sense. Both bodies technically orbit a shared balance point, but because the Sun is so much more massive, that balance point usually lies very near or within the Sun itself. The system is overwhelmingly centered on the star. To look at Earth's orbit from this level is to see the planet's smallness in an unusually clear way. Earth is not merely smaller than the Sun in body. Its whole annual path, though vast in human terms, is just one narrow track in the Sun's much larger domain. The star shines across a system extending far beyond Earth, and its gravity holds planets, smaller bodies, dust, and distant icy populations in ordered motion. Earth's significance for life does not alter its modest physical rank. It is one small world moving at one astronomical unit around an ordinary star. Seen from the scale of the Sun and Earth's orbit, the solar system becomes unmistakably star-centered. The Sun supplies nearly all the mass, nearly all the energy, and the gravitational order that makes Earth's yearly path possible. Earth circles within that order as a small rocky planet at a favorable distance, but it never approaches parity with the star it orbits. Against the Sun's size, mass, and power, Earth is not a central body. It is a tiny companion moving continuously around the dominant heart of the solar system. Within the Sun-centered system, the next inward region is the Earth-Moon system. Here the scale narrows from star and orbit to a two-body partnership in which one planet and one large natural satellite move together under gravity. The Moon is much smaller than Earth, yet it is large compared with its parent planet in a way that is unusual among the major planets of the solar system. This makes the Earth-Moon pair an especially revealing step in the inward path of scale. Earth is no longer one small planet among several inner worlds. It becomes the larger member of a local orbital pair. Even so, it does not stand alone. It is accompanied by a world substantial enough to shape tides, stabilize the tilt of Earth's axis over long spans, and define a shared motion through space. The Moon's diameter is about 3,474 kilometers, a little more than 1/4 of Earth's diameter. Its mass is much smaller than Earth's, about 1/81st as great, but its apparent size in the sky gives a stronger visual presence than those numbers alone might suggest. This is because the Moon is close. On average, it orbits about 384,400 kilometers from Earth. That distance is large enough to fit all the other planets only in imagination, yet small enough in astronomical terms for the Moon to dominate the night sky and to remain the only world beyond Earth reached by human footsteps. The Earth-Moon system therefore carries a dual character. It is intimate by cosmic standards and still immense by human ones. The Moon does not circle Earth in the way a small object circles a fixed central point. Both Earth and Moon orbit a shared centre of mass, the balance point determined by their masses and separation. Because Earth is much more massive, this balance point usually lies inside Earth, but not at Earth's exact centre. As a result, Earth itself performs a small monthly motion as the two bodies revolve together. This detail does not disturb daily life, yet it matters scientifically because it shows that even in the closest familiar celestial relationship, motion is shared rather than one-sided. Earth is the dominant member of the pair, but it is still part of a partnership governed by mutual gravity. The Moon keeps the same face toward Earth because its rotation period matches its orbital period. This state is called tidal locking. It means that as the Moon rotates once on its axis, it also completes one orbit around Earth, so the same hemisphere generally remains turned inward. The far side of the Moon is therefore not permanently dark. It receives sunlight just as the near side does, but it faces away from Earth through the orbit. This steady orientation adds to the sense that the Earth-Moon system is dynamically mature, shaped over long spans by gravitational interaction. The locking results from tides raised in the Moon early in its history, which gradually slow its rotation until the present configuration is reached. Tides connect the two bodies continuously. The Moon's gravity pulls more strongly on the side of Earth nearest to it and less strongly on the far side, creating the familiar tidal bulges in the oceans. The Sun also contributes to tides, but the Moon plays the larger role because of its closeness. As Earth rotates, coastlines move through these bulges, producing the changing rise and fall of sea level. Tidal friction slowly transfers angular momentum from Earth's rotation to the Moon's orbit. This causes Earth's day to lengthen very gradually over immense spans of time while the Moon slowly recedes from Earth by a few centimeters each year. Laser measurements from reflectors placed on the Moon confirm this recession with great precision. The Earth-Moon system is therefore not fixed. It evolves slowly, with measurable change unfolding across deep time. The origin of the Moon is most consistently explained by the giant impact model. Observations and simulations indicate that early in solar system history, a Mars-sized body collides with the young Earth, ejecting material that later gathers to form the Moon. This model fits the large size of the Moon relative to Earth, the low iron content of the Moon compared with Earth as a whole, and important aspects of the chemical similarity between lunar and terrestrial rocks. Some details remain under study, especially the exact character of the collision and the mixing of material afterward. But the broad picture is well supported. The Moon is not a captured wandering object in the most accepted account. It forms from the same violent early history that helps shape Earth itself. The physical contrast between the two worlds remains clear. Earth has a thick atmosphere, liquid water on its surface, active weather, and ongoing plate tectonics. The Moon has no substantial atmosphere, no stable liquid water on its sunlit surface, and no present plate tectonics comparable to Earth's. Its surface preserves craters, volcanic plains, highlands, and ancient scars far older than most of Earth's visible crust. Earth renews much of its surface through erosion, tectonic movement, and sedimentation. The Moon preserves a more static record. In this way, the pair offers two different outcomes from related beginnings. Earth is geologically and climatically active. The Moon is quieter and more slowly changing. Yet the Earth-Moon system is not only a contrast of surfaces, it is also a moving pair travelling together around the Sun. While the Moon orbits Earth, both bodies simultaneously orbit the Sun at high speed. The Moon's path through space is therefore not a simple loop that falls backward. It is a smooth forward-moving curve that always bends around the Sun while wavering around Earth's orbital track. This shared motion places the Earth-Moon pair within a larger hierarchy. The Moon belongs to Earth, and Earth belongs to the Sun. Scale becomes nested once again. Even at this close level, Earth is not isolated. The Moon also changes how Earth appears when viewed from outside. From far enough away, the pair can be recognized as a planet-satellite system with an unusually large companion. From the Moon, Earth appears large in the sky, far larger than the Moon appears from Earth. This reversed view does not enlarge Earth in any absolute sense, but it sharpens its identity as one world among worlds. Earth becomes a globe with phases, reflected light, cloud bands, and a finite curved surface, visibly partnered with another orbiting body. The Earth-Moon system turns the human homeworld into one member of a visible celestial pair. Seen at this scale, Earth is larger than before, yet not solitary. It stands as the primary body in a two-world system separated by hundreds of thousands of kilometers, joined by tides, shared motion, and a long common history. The Moon is small beside Earth, but large enough to matter constantly. Against the wider backdrop of the solar system, the Earth-Moon pair is still minor, within its own local region. However, it reveals that Earth itself is part of an orbital relationship, a planet accompanied by a substantial companion in a quiet and enduring gravitational dance. After the Earth-Moon system, the next inward region is Earth itself as a whole world. Seen from space, Earth is no longer the hidden planet inside a larger orbit, but a complete globe with a measurable size, a curved surface, and a thin envelope of air wrapped around rock and water. This view changes the sense of scale in a quiet but decisive way. From the ground, the planet often feels limitless because the horizon is local and the surface beneath human life appears broad and flat. From space, that impression falls away. Earth becomes finite, rounded, and clearly bounded. Its continents and oceans lie across a sphere only about 12,742 kilometers wide, substantial on human terms and still small beside the wider scales already crossed. Earth is the largest of the rocky planets in the solar system, though only slightly larger than Venus. Its nearly spherical shape comes from gravity pulling matter inward strongly enough that large irregularities cannot remain across the whole body. The planet is not a perfect sphere. Rotation causes a slight equatorial bulge, making Earth a little wider at the equator than from pole to pole. Earth rotates once in about 24 hours, and that steady spin defines the daily cycle of light and darkness over the globe. From outside, the most striking visual fact about Earth is the dominance of water. The oceans cover about 71% of the surface. They form one connected global body divided by continents and shaped by currents, coastlines, and seafloor structure. The blue appearance of Earth from space comes largely from water and from the way the atmosphere scatters light. The continents interrupt the oceans with varied forms of land, from wide plains to long mountain belts, dry deserts, forests, and ice-covered regions. Clouds drift above both, often obscuring the surface below and showing that Earth is not a static map but a changing climate system in constant motion. The atmosphere is thin compared with the size of the planet. Nearly all weather, most clouds, and the air directly involved in life near the surface are confined to a very shallow layer on planetary scale. This thinness is one of the clearest signs of Earth's smallness as a world. The atmosphere feels immense from the ground because it extends upward beyond ordinary reach. But when seen against the full diameter of Earth, it resembles a delicate skin. The The same is true of the oceans. Even the deepest trenches are minor scratches compared with the radius of the whole planet. The surface systems that matter most to life occupy only a narrow outer fraction of Earth's total body. Polar ice, seasonal snow, and shifting cloud systems add changing brightness to the globe. The white polar caps and ice sheets at high latitudes reflect large amounts of sunlight and help regulate climate. Sea ice grows and retreats with the seasons. Clouds move in bands, spirals, and broken fields shaped by winds, ocean temperatures, planetary rotation, and the uneven heating of the surface by sunlight. From space, these patterns make Earth look active in a strictly physical sense. The atmosphere circulates, water evaporates and condenses, and energy is transported from one region to another. Earth also shines in another subtle way. Its brightness changes depending on cloud cover, ice, land, ocean, and viewing angle. Sunlight reflected from the planet can illuminate the dark part of the moon, producing earthshine. This faint light seen on the lunar surface is a reminder that Earth itself is a luminous object when viewed from elsewhere, not because it generates its own visible light, but because it reflects sunlight into space. In the context of planetary science, Earth is one reflective globe among others, though its combination of water, air, clouds, and surface chemistry gives it a distinct appearance. The surface is not fixed over deep time. Continents move slowly because Earth's outer rocky shell is broken into tectonic plates. These plates drift over the deeper mantle, carrying continents, opening oceans, raising mountain ranges, and driving earthquakes and volcanism. The motion is extremely slow in human terms, usually measured in centimeters per year, yet over millions of years it reorganizes the face of the planet. Seen as a whole world, Earth is not simply a finished sphere. It is a geologically active body whose surface changes through internal heat, erosion, and the circulation of water and air. The magnetic field is another whole planet feature, generated largely by motions in the liquid outer core. It extends outward into space and helps deflect many charged particles arriving from the Sun. It does not create a visible shell around Earth in ordinary sight, but it is part of the planet's physical identity as a world. The magnetic field and atmosphere together help protect the surface environment from some harmful solar and cosmic radiation. These protections are not absolute, but they are important. They show that Earth's habitability depends not only on surface conditions but on whole planet properties rooted deep inside its structure. To see Earth as a world is also to recognize its limits. There is no endless land and no infinite sky. There is a closed globe with finite area, finite oceans, a finite atmosphere, and a surface shaped by constraints. Every forest, river, city, desert, and mountain exists on one continuous planetary skin. The human sense of vastness on the ground remains real at local scale, but space reveals its boundary. This view does not make Earth unimportant, it makes it proportionate. Earth is large enough to sustain oceans, weather, geology, and life, yet small enough to be crossed by light in a fraction of a second, circled by aircraft in less than 2 days, and seen whole from nearby space. It is a real planet, not an abstract point, but it is still a compact globe in cosmic terms. Its beauty from orbit arises partly from that wholeness: blue water, white clouds, brown and green land, and a thin, bright edge of atmosphere around a dark background. Seen at this scale, Earth becomes a complete but limited world. The planet is not an endless stage beneath human life. It is a bounded sphere of rock, water, air, ice, and motion, turning in sunlight with a thin, active surface wrapped around a deeper interior, against the larger systems beyond it. Earth remains small. Within its own planetary identity, however, it stands as a whole world, finite, dynamic, and fully contained within one shining globe. On the surface of Earth, scale changes once more. After the great measures of galaxies, stars, orbits, and planets, the final inward region is the thin inhabited layer where human life unfolds. This layer is not a separate shell in the geological sense. It is the narrow meeting place of land, ocean, air, ice, and living things. Almost everything familiar to human experience exists here, close to the boundary between the solid planet below and the atmosphere above. From the ground, this region can seem vast beyond measure. From the scale of Earth as a whole, it is extraordinarily thin. Human life does not occupy the planet in depth. It occupies a surface film, a delicate outer margin on one small world. The curved globe that appears complete from space becomes, at human scale, a set of local landscapes. Plains stretch to horizons, mountain ranges rise above valleys, coastlines divide land from sea, rivers cut through rock and sediment, forests, grasslands, deserts, and cities spread across different climates. Yet all of these features lie on a planetary skin. Everest rises less than 9 kilometers above sea level. The deepest ocean trench descends about 11 kilometers below it. Set against Earth's radius of more than 6,300 kilometers, both extremes are slight. The tallest mountains and deepest trenches barely disturb the roundness of the planet. What seems enormous from the ground remains shallow when measured against the size of Earth itself. The same is true of the atmosphere that supports breathing, clouds, and weather. The full atmosphere extends far upward in a gradual thinning, but most of its mass lies close to the surface. Human bodies live in the densest, lowest part, where air pressure remains high enough for ordinary breathing and temperatures allow liquid water to persist widely. Aircraft cruise in a narrow band of the lower atmosphere. Weather systems, though they tower dramatically over landscapes, are confined to a layer thin compared with the diameter of the planet. Thunderstorms, jet streams, fog, rainfall, and wind all belong to this shallow moving envelope wrapped around Earth like a transparent film. The oceans also reveal how little of the planet is directly accessible. From above, they dominate Earth's appearance. From the point of view of total planetary structure, they are very thin. The average ocean depth is only a few kilometers. Even where water is deepest, it does not begin to approach the depth of Earth's interior layers. The seafloor itself forms part of the outer crust, and below it lie far thicker regions of rock extending downward into the mantle. Human navigation crosses the sea surface easily compared with the difficulty of descending far into the ocean or drilling deep into Earth. The inhabited world is not only shallow, it is restricted to a very narrow outer interface. Human structures emphasize this restriction. Cities rise upward in towers and spread outward in roads, ports, fields, and suburbs. Yet their height and depth remain minute on planetary terms. Even the tallest buildings are negligible against mountain height, and mountains are negligible against Earth's radius. The deepest mines and boreholes penetrate only a tiny fraction of the crust. Most human movement stays within a few kilometers above sea level, and almost none of it reaches far downward into the solid planet. The species lives on the surface in a literal sense. It alters the land, cultivates soil, diverts rivers, builds coasts, and fills the air with aircraft. But it does so within a layer so thin that the whole human sphere could be mistaken for a faint surface effect when Earth is viewed as a planet. This final measure brings the meaning of smallness into the most immediate form. Earth is small beside the Sun, the galaxy, and the observable universe. Human life is small beside Earth in the same way that weather is small beside the whole atmosphere. A city that contains millions of people can disappear from sight within a region of cloud. A nation can vanish on a globe. The total land area occupied by buildings, roads, farms, and ports remains only a modification of the outermost surface. Even the human timeline is thin. Recorded history spans only a tiny instant compared with Earth's age of about 4.5 billion years. Civilizations rise and change while continents drift almost imperceptibly beneath them. Life in general also gathers near the surface. Some organisms live deep underground, some high in the atmosphere, and many in the deep ocean. Yet the biosphere as a whole still occupies only a narrow planetary margin. The biosphere is the zone where life exists. On Earth it extends through parts of the lower atmosphere, across the land surface, through soils, and through the oceans down to great depth. But compared with the full size of the planet, it is astonishingly slight. Most known life depends directly or indirectly on sunlight, liquid water, and chemical cycling near the surface. The deep interior remains hot, compressed, and largely unreachable to living systems familiar at the surface. Human perception often reverses this proportion. The ground feels central because life stands on it. The sky feels immense because it rises overhead without visible support. Distances between cities or across oceans feel monumental because the body crosses them slowly. These impressions are real at local scale, but they are not the final measure. Earth's surface is not a boundless stage. It is the outer boundary of a planet with finite circumference, finite area, finite atmosphere, and finite resources. Human life occupies it as a temporary and active presence, but not as a dominant physical mass. Seen in this final inward way, Earth becomes both larger and smaller at once. It is larger than daily life suggests because it is a whole planet beneath every local horizon. It is smaller than daily life suggests because the region that contains human experience is only a thin external layer on a globe already modest in the solar system and minute in the cosmos. A person stands on the skin of a rocky sphere, under a shallow ocean of air, beside water and stone that form a tiny fraction of the planet's full body. That person belongs to cities, histories, and landscapes that feel enormous within human life and nearly vanish when measured against Earth as a world. The universe's true scale is therefore not revealed only by moving outward to galaxies and beyond. It is also revealed by returning inward and finding that the familiar human realm is confined to a narrow surface film on one small planet. Earth is not the centre of the cosmos, and the human world is not even the greater part of Earth. It is a brief living layer at the edge of rock, water, and air, resting quietly on a globe that is itself almost lost in the vastness beyond. Far above the local horizon, beyond clouds and weather, beyond the moon and the planets, beyond the quiet lanes of the Milky Way and the distant gathering of galaxies, the scale of the universe settles into a simple truth. Earth is real, whole, and precious, yet physically very small. Its diameter is modest beside the Sun. Its orbit is modest beside the solar system. The solar system is modest beside the galaxy. The galaxy is modest beside the wider structures of the observable universe. At every larger level, the familiar world grows quieter and less central, and yet the return inward changes the feeling of that smallness. Earth is not less because it is small. It is simply limited, finite, and contained. Its air forms a thin outer veil. Its oceans spread across a shallow surface. Its mountains rise only slightly on the scale of the globe. Human life moves across an even thinner layer, between rock below and sky above, living within short spans of time on a planet already small against the dark. This is the calm proportion that astronomy offers. It removes the illusion of central size, but it also removes confusion. The world does not need to be large to be complete. It does not need to fill the cosmos to matter within its own boundaries. Earth remains one small sphere of water, stone, air, and life, turning in sunlight, carried through space without fanfare. Around it extends a universe too broad for instinct and too deep for ordinary measure. Within it rests one inhabited surface, quiet and brief, held on the outer skin of a small world. In that balance between vastness and finiteness, the scale of Earth becomes clear. It is little in the cosmos, and still entirely a world.